So thanks for having me here. It's always a pleasure. So the question that we want to, why is it actually so interesting to look at nu equals 12/5? Well, one of the big questions that we have is, of course, which topological phases of matter actually occur in nature. And, as we'll see, the 12/5 quantum Hall state is a particularly interesting playground for that topic because there's at least several candidates, so that'll be worth looking at. And another important question, of course, coming from mission Q is, can we attain fully topologically protected quantum computation from the states that actually do occur, the topological phases that actually do occur in nature. And another reason is, of course, more important than these, is that we're actually going to have experiments that are going to be probing the nature of these second Landau level quantum Hall states very soon. So right now, the ones that really probe the details of them is still kind of out of reach for getting at the 12/5 state, but we expect pretty soon we'll have experiments looking at these. So I'll say something about that. Now, this is the one-slide crash course on quantum Hall effect, which basically you have a two-dimensional electron gas in a large magnetic field perpendicular to the plane, and you take it down to low temperatures, and amazingly these gapped incompressible quantum Hall liquids show up at these quantized filling fractions, and they have this wonderful property of having fractionally charged quasiparticles which carry non-trivial statistics that are anyonic. So you expect that most of the filling fractions have abelian anyons, meaning if you just do particle exchange, you'll pick up some phase factor on the wave function. But we also expect that a number of them will also have non-abelian anyonic statistics. In particular, here's the nice plot from Xie et al. Of the second Landau level Hall trace. We can see that to bring your attention to the filling fractions that we have well developed Hall plateaus at, we have, of course, the 5/2 state here, the 7/3 state here, 8/3, and the 12/5. And if we look over here, we can see what seems to be a developing 3/8 state, which you have a nice plateau here if you manage to tilt the trace over and level this thing out. And so anyway, the point is that there's a lot of interesting physics going on in the second Landau level, which we don't really understand, but are really beginning to make progress on. And so before we have a firm understanding, it's of course good to have as many viable candidates for the observed states. And, well, in the past there's been Laughlin states, the Halperin states, the Moore-Reed and the Reader-Zei states. And notable success is that even though we don't have, what some people would call completely indisputable evidence that the Moore-Reed state describes the 5/2 filling fraction, there is a large amount of numerical evidence and now an accumulating body of experimental evidence that strongly supports Moore-Reed or its particle conjugate as the correct description of the 5/2 state. So this is relatively well understood, state in the second Landau level. And of course, the important prediction from this Moore-Reed state is that it leads us to believe in the existence of non-abelian anyons. So the question now that I'll address is, what about 12/5 and other plateaus that you see in the second Landau level? Well, here is just an accumulation of the gaps that have been measured experimentally for these various second Landau level filling fractions. And in particular, the thing to notice is that generally the 5/2 state is the strongest. It's the first plateau that appears when you start looking in the second Landau level, and then from there, the 7/3 and 8/3 are typically the next strongest, and in most samples, the 8/3 actually has about half the gap of the 7/3, but in some, they actually have roughly even gaps.
So what does a unit say?
No.
What are two numbers on the gaps?
Two numbers?
Delta one.
The subscripts were to indicate what reference it comes from, but
Alright.
it's not shown here, so I just yanked it from my paper. But it's some combination of these. Okay, so in any case, there's also some numerical work that's indicated that the quantum Hall states that you observe between the 7/3 and 8/3 filling fractions, they have a non-Laughlin type character with pairing or clustering that's reminiscent of what you see at the 5/2 state. And outside of this region, what you see is Laughlin-like correlations in the electrons. And so you expect maybe that this 14/5 is just going to be some Laughlin state. So, but in any case, what we know about the lowest Landau level is that the Haldane-Halperin states, and especially their composite fermion description, seems to work quite well in describing these, at least numerically speaking. I wouldn't say we have any experimental evidence that says that they necessarily are the description for all the states. There's at least some strong belief that this is a very good description. So the natural question is, can we construct a hierarchy similar to the Haldane-Halperin construction built on this strongest 5/2 second Landau level state? So let's think about what the hierarchy picture, what actually happens when you're doing this hierarchy construction. So you start with some quantum Hall state, and it can be non-abelian if you like, and so you write down its ground state wave function, and then you introduce quasi-particles, which, when I say quasi-particles, I mean quasi-holes or quasi-electrons, so it's more general than just quasi-electrons, but you introduce some quasi-particles into the wave function, but so this will change the density. So over here on the right, I'm kind of having a schematic representation of the density profile of the quantum Hall liquid. And so you introduce quasi-particles, you change the density profile, but it's done in a localized manner where you just change the density where you have the quasi-particles. So this obviously isn't quite what we want to produce a new quantum Hall state. So the next step is to project these quasi-particles that you've introduced onto a new quantum Hall state. And in particular, you want this quantum Hall state to be something that is a good incompressible state, so that you will you'll delocalize these quasi-particles and produce a uniform incompressible gas at a new filling fraction. So with the wave functions, that means you put in, I guess you'd call this a pseudo wave function, phi star here, and then you take an integral over all the coordinates of the quasi-holes or electrons, and that'll give you a new state. So here is the standard example from the past is the Haldane-Halperin states. You, for example, start with the Laughlin state, which has the the famous wave function, which is just, and this is described by you can think of as a U1 Chern-Simons or conformal field theory, and then you add quasi-electrons here. Now here I'm just using the Laughlin form of the quasi-electrons, but you could use something like the Jane quasi-electron or whatever you wish. But this is particularly nice because it keeps the statistical part of the quasi-electron wave function explicit on this. And then you multiply this wave function by this pseudo wave function, which is picked in particular in a way that this power here combines with this power here in order to give you bosonic statistics of your quasi-electrons, and in that way you end up with a single valued wave function here, which now you can just freely integrate over the quasi-electron coordinates, and it gives you a new state at the 2/5 filling fraction. So now we can think of this as being a potential candidate for the 12/5 state as well, by just leaving the two filled lambda levels as something you treat as underneath this. And now you go in this way. You go from this U1 with a subscript 3 on it to a U1 with a K matrix, where the way you read off this K matrix is that the 3 is this original 3 right here. The -1 has to do with this being essentially a -1. The quasi. If you were to put in quasi poles here, you'd have a +1, and then the 2 is just when you combine this 5/3 with this 1/3, you end up with the power of 2. So these states also have a composite fermion picture, which we've heard about earlier. So I'll just kind of rush through it. And basically the idea here is that you have n filled lambda levels, where I put a plus or minus indicating that they can be having a different orientation with respect to the magnetic field, and you put in 2p vortices, which you attach to each one of these fermions, and you do that by introducing 2p Jastrow factors. Now, of course, when you have n-filled lambda levels, you don't have a lowest lambda level wave function, and so the last step is something which is a very important and highly non-trivial step, is projection onto the lowest lambda level, and this gives you a state which is essentially equivalent to the hierarchy construction. And it's easy here to read off the filling fractions. You get u equals n over 2pn plus or minus 1. And in particular, the 2/5 composite fermion state is just two vortices attached to two filled lambda levels. So now let's look at the Moore-Reed state, and to try to understand how to apply a hierarchy construction to it. So the Moore-Reed state can be described as an Ising sector times the U1 charge sector with a restriction of the quasi-particle spectrum. In particular, the Ising sector carries three types of topological charge: the trivial I charge, the psi charge, and the sigma charge. And the U1 is just the charge sector, and so you have fluxes that you can. It gives you fluxes, but here you actually are going to be allowed to have half-integer fluxes. In the case that your Ising sector is a sigma, so if you have a sigma charge, then you can have a half-integer flux attached to it. Otherwise, if you have an I or a psi, you have to have an integer flux, just like the standard Laughlin states. And in particular, though, the electrons in the Moore-Reed state will carry the psi charge and two fluxes. So the psi charge is what gives you the Faffian term that you presumably are all familiar with, and encodes the fact that you have P plus IP pairing in this state, and the two fluxes just give you two Jastrow factors over here. So this is the ground state of the Moore-Reed state. And now to build a hierarchy on this state, we just want to follow exactly the same steps. You put in quasi-particles and project them onto a new quantum Hall state. So, of course, the amazing thing about Morita is that it has non-abelian quasi-particles. The E/4 quasi-pole, fundamental quasi-poles carry the sigma charge and the half flux. And these have two fusion channels. So if you combine a pair of sigmas, they can either give you the I or the psi charge back. So, we can think about what happens if we just wanted to form a gas of these E/4 non-abelian quasi-particles. And actually, you can do this in a mathematically well-defined way, like we did before, by forming trivial representations of the braid group. However, physically speaking, there's problems with trying to approach this in this way. And in particular, if you just try and form a gas of these E/4s and condense them, then the next layer that you introduce, the particles or the electrons of the next layer, they have to be non-abelian in order to compensate for this sigma that the fact that these quasi-particles are non-abelian. And that's so technically speaking, the way you do it is you introduce, say, a conjugate sigma, and then sum over all of the fusion channels, and then that gives you a trivial braid group representation. But a gas of these non-abelian quasi-particles is going to be, they're going to be strongly interacting because they're not well separated, and so the non-abelian degeneracy that you have, it can't really be preserved anymore when you have strong interactions between non-abelian and quasi-particles. You'll split the different fusion channels, and so it's not clear that you can do this in a physically meaningful way. And furthermore, if you do this, the result that you get is likely not going to be incompressible, because if you think about the next layer, whether or not it's incompressible, it seems almost certain that it's not, because you're forming a gas that has a highly degenerate state space, even if you were to maintain the non-abelian degeneracy. And then, another very significant problem with this is, of course, if you just said, well, who cares, let's just go ahead with this construction, fine, you end up with filling fractions that are experimentally non-existent in the second Mandel level, like 8/17ths and 6/13ths. And also the states you end up with, because you did this pairing of sigmas and making them into trivial braid group representations, is you end up with states that are abelian and appear to have the same universality class as others. So this was what basically what Levin and Halperin's construction was that you were asking about yesterday. So what Joost and I did was say, well, let's assume that if you do have this kind of gas of quasi-particles, because they're strongly interacting, they're going to want to pair up into some preferred fusion channels and form a gas of bound pairs. So this was kind of the physical picture we had in mind when we started doing this. Now you don't actually have to even think of it as that way. You can just think of it as you just start with E/2 quasi-particles, which are Laughlin-like quasi-particles in this theory, and just carrying one flux.
But this is an assumption that is not. So how do you justify that? That the effect of interaction is that these pairs are formed. Why pairs, not bouncing of 10 particles?
Well,
Some
because
interesting
energetically speaking, you expect that charge doesn't like to bunch up into higher charge composites.
No, we know from solid state physics very well that pairwise interactions don't always end up in darker states. You can form all kinds of collective states.
Well,
Why the simplest possible choice?
Why not the simplest possible choice?
Why not? Because we see that this is not happening all the time.
It's the first thing to try.
Yeah, but it's a crucial assumption here that it's not justified. standardization?
Well, I think we actually do know, typically speaking, that the lowest energy excitations in quantum Hall states are the lowest, right?
It's not clear at 2/5 whether the bound quasi-Hall state, two quasi-holes binding together to form a 2/5 Hall charge, is not the lowest energy excitation. It's not clear. It's difficult to say because the difference of the energy between two widely separated and the bound one is very close. And if you don't know how to extrapolate to the thermodynamic limit very well for the two really unbound pairs, it's subtle.
Yeah, sure.
But
that actually supports my case, though,
half,
because the 2/5 quasi-particle in the 2/5 state is the Laughlin type quasi-particle.
However, at 5/2, we really don't seem to see these bound pairs
No, but
for normal Coulomb interaction.
you're also not putting in a gas, right? I mean,
Oh,
you expect that once you actually are putting enough density to go to a different
right.
filling fraction, things change.
Yes.
And I'm saying, of course, there's an assumption being made here.
It's just
But
the
let's just run with
elementary
it and see what happens,
excitation.
you know?
The elementary excitation seems to be single quasi-holes of charge 1/4. That's
Yeah, of course.
the message
Yeah.
from numerics, I think.
Maybe another remark to be made is that, like, really what we're saying is that there are some composite excitation which condenses, which has to be one of the 12 types of excitations that is there in this state, and so you have to choose one that actually behaves like an abelian particle, and then you don't have much choice anymore. It doesn't really matter if it's a pair or or some other complicated multi-particle composite which happens to have this charge and this
Right.
logical behavior.
Right. But all that aside, this is also the most like the original hierarchy construction. You're
Yeah.
just condensing
It's
Laughlin
the
type
obvious thing to
quasi-particles.
try.
It's completely the obvious thing. So, in any case, this is what we're gonna take as our quasi-particles forming this gas and see what we get. Okay, so you start with the Moree state, add in these E/2 abelian quasi-particles, which carry only a flux in the charge sector and trivial charge in the Ising sector. And in terms of the wave function, that's just as, it looks exactly like putting in Laughlin quasi-holes into Laughlin states. You just pick up a vortex here with respect to the electrons, and now we want to project this state into a new quantum Hall state, and we can do this as before by taking that state and putting in a appropriately chosen pseudo wave function which has statistics that cancels out. So you had this 1/2 up here, so you want to have something that cancels the 1/2 and leaves you with bosonic statistics. So this is 2 plus 1/2 and cancels that out. And then you perform this projection where you integrate, and you get a wave function like this, and it turns out that this gives you a 2/5 state right away. And so here's the K matrix appropriate to that. You can see it's basically just doing the exact same type of hierarchy construction on the charge sector of the Moree state. So similarly, you can do condensation of quasi-electrons, the E/2 quasi-electrons for the Moree state. And if you go ahead and do that in just exactly the same way, you end up with a 2/3 state. And you can also try to produce states at 1/3 filling fraction. Well, the easy way is, of course, just take the particle conjugate of your 2/3 state, and you'll get a 1/3 state. But another option could be that you condense the quasi-holes in the side channel instead of in the trivial channel. And in this case, you're going to want, because now the quasi-holes have an additional -1 in their exchange coming from the side topological charge that they carry, you'll put in a different pseudo wave function. So here you would end up with instead of an even integer in this component of the K matrix, you'd have an odd integer, and that gives you a 1/3 state. So how about other filling fractions? Well, if you just continue down the hierarchy of the 2/5 construction to the next level of hierarchy, you'll end up with a 3/8 state, which was this one that seemed like it was developing potentially. Who knows if it actually will or not. And if you follow down the chain of the 2/3 construction 2 more levels, you'll end up with a 4/5 state, which was this, the 14/5. Even though we expect it'll probably be abelian, this is just showing that we can indeed produce a state at this filling fraction. Now, a nice thing about these constructions is also that it has a composite fermion type picture similar to the abelian hierarchy states. And in particular, here's the construction for, you can basically start with a Pfaffian times some number of Jastros and plus or minus n filled lambda levels, and then do this kind of projection like you would for the composite fermion. And here you end up with filling fractions that are n/3n-1, which is the 1/3, 2/5, 3/8, and so on sequence of states that you got in the hierarchy. And here you'll have a n/n+1 sequence, which is the 1/2, 2/3, 3/4, 4/5 sequence. And this is essentially, to translate from an equivalent picture as the composite fermions, here you not only attach a U1 Chern-Simons flux to your integer quantum Hall states, you also attach a SU2 level 2 flux to them. Now, of course, we also should all be more or less familiar with the Reader's eye states, which are the ZK parafermions. And here we form states by ascribing a parafermionic field to the electrons, and then just forming the natural states you get by putting on Jasper factors that give you the appropriate statistics for the electrons. And this gives rise to a sequence of states which is given by k/k+2, and in particular the 1/3 state here is just the Laughlin, and the 1/2 is just the Moore-Reed, and then k=3 is the famous Fibonacci type Reader's eye state, and so on. And you can also, of course, just take the particle conjugate of these states and end up with the sequence of states at 2/k+2. So now, in this way, we produce a 12/5 candidate from the Reader's eye states. They produce it, I should say. And the particularly nice thing about the k=3 states, or state, is that they have Fibonacci type anyons, which are computationally universal. Their braiding is computationally universal, and so they would be very useful for topological quantum computation. Now, of course, the important question to address is, how do we know what will actually exist? Now, we can start from numerical evidence, which has been used from the very beginning of fractional quantum Hall theory. And in particular, there's a long list of people who have done very good numerics, and two of them I've been collaborating with, Adrian Fagan and Victor Muller. So I'll give just a quick kind of review of Reed and Rezai's numerics. So what they found was, looking at the 13/5 filling fraction on a sphere, they found that they end up with pretty good overlaps near the Coulomb point. So the horizontal axis is delta V1, changing the V1 pseudopotential. And for n equals 15 electrons, they would get something like 97% overlap, and for n equals 18, they'd get 88. And here is some work that they've done on the torus. So they've basically varied both delta V1 and delta V3 here, and they because there's two ground states on the torus for the Reader's Eye, they're looking at actually overlaps between two states, and coming up with the total of these two states, that is 1.6. So that's roughly 80%, I guess, is the interpretation there. It's their peak overlaps for n equals 15. Here is a plot of the spectra that they get for the torus at 18 electron size, system size, and they can see here that the in this region near the Coulomb point, you end up with this kind of twofold degeneracy on the torus, which seems to be indicative of the Reed-Rezai states as being the appropriate ground state. So now here's some numerics that Gunnar Moller and Adrian have done. So the first thing that we've looked at is basically computing gaps, just the charge gaps at 12/5 on the sphere, and looking at the various different flux values so that you can compare states at different shifts, which are given by this formula here, where you relate the number of flux that you're looking at on the sphere to a filling fraction, a particular filling fraction, which is then modified by what shift you're at, and in particular, you can identify the states that you're seeing in this way as, this flux value here should correspond to the same shift 2 of the VS state that we've proposed for 2/5, and over here at shift -2 is where the Reed-Rezai state would occur, and then over here at shift equals 4 is the Haldane-Halpern state. So you can see that, well, it doesn't appear that there's a gapped state here at in the second lambda level for the hierarchy state shift. And here is a more detailed plot of these three shifts, where we also vary V1, and what we find is that, of course, if you vary V1 high enough, then both the ES and the Reed-Rezai states will become gapless, and the gap for the hierarchy state becomes positive. So you stabilize the hierarchy state if you change V1 to be large enough. But then there's some nice region around the Coulomb point which has the BS and the Reed-Rezai states being as gapless. So now we can also look at the correlation function at shift equals 2, and what we find for 12, 14, and 16 electron sizes is a very nice sort of flat correlation function in the long distance, and kind of a shoulder here in the short end, which is supposed to be indicative of abelian states, but you know, take from that what you want.
How does that figure compare to the other two sheets?
So actually, we didn't look at that, but you know, I think Reed and Razai have a picture of the Reed and Razai states. It looks fairly similar.
So can you go back to the previous slide, please? Did you compute the q to the fourth coefficient in that? Or?
No.
Because
There
that
seems,
doesn't tell you.
there seems to be some kind of non-uniform behavior between 12,
Yeah.
14 and 16.
Yeah.
14 seems to be somewhat anomalous.
Yeah. I think so.
Is that the Coulomb point exactly, or is it V1,
Yeah, this is
V1
point
delta V1 equals 0?
There's probably a 2 times even and 2 times odd effect.
Yeah, n equal 10, you have no results.
That could be.
I think we have them. I don't know if we looked at them.
And this is on the disk.
Sphere.
No, that's
okay,
sphere.
good. Then okay, where data equals
So we can also look at overlaps and you know, just using the straight using the composite fermion form of the wave function. Let's see. So using this form of the wave function here, we compute the overlaps on the sphere, and what we find is, you know, for these 4 system sizes, we find pretty darn good overlaps at the n equals 8, and still it remains fairly high. You know, I think always above 80%. So it's pretty good. But then, you know, we can use Gunnar and Steve Simon's trick of optimizing the pairing wave function in the Faffian. So you replace the Faffian with some p-wave, a p-wave wave function which has some variables which you can optimize, so you have an actual variational wave function. And by optimizing that, we end up with, of course, still a p-wave, a p plus ip state, but we can also increase the overlaps, and in particular, for our largest system size, we get, you know, 92% overlap, where we have 1 not, let's see, that's 19 billion states in the.
That cannot happen.
What's that?
It's
It's
not
LZ equal to 0.
Oh,
LZ.
sorry, LZ.
Factor 10,000.
Yeah, okay.
Can you use the same trick for redesign?
No, we don't know any general sizes which would be in the same phase.
Well, you might.
So
Yeah, it's not known whether there's an equivalent type of optimization.
Presumably that also includes the optimization.
But this optimizes the hardcore. This thing that optimize the. Is it a variation on the short distance scale, right? Or what's the variation?
Every short distance is a finite size system.
No, but yeah. Right.
Changes the pair wave function.
it's
Right.
most the biggest changes are between 1 and
Sorry.
the biggest changes of correlation functions occur between something like 1 and I think. The short distance, very short distance behavior is almost untouched because that's mostly defined by the flux attachment. But then we'll have like pair separations, class separation functions, couple of
I'm just wondering what the variational parameters
It's
are.
interesting. The question
Well,
whether
they're best expressed in terms of occupation.
with the same.
Okay. So, you know, so now we've established that the BS wave function seems to be a pretty good description of the states observing at shift equals 2. So now the natural thing is to try to compare these states at shift equals 2 with the states at shift equals minus 2 to see, you know, which one of them is sort of the winner in the thermodynamic limit. And so to do this, we've tried to carry out a thermodynamic scaling of these finite systems, of the finite system's ground state energies. And so this top line here is the higher Halpern states, and we should not really worry about that too much because it's actually not even incompressible. But this is the shift equals 2 state, and this is the minus 2. And what we find is, you know, basically they extrapolate to values that are very, very close to each other.
If you throw out the smallest point, it certainly looks like.
No, of course, if you throw out the smallest point, but you know, you also have to
It
have
looks like it's really
you have to have a systematic reason for throwing out data. I mean,
Well, it's the smallest. That's pretty systematic.
well, I mean, I can go to.
The rest of them seem to look like they're.
No, but I can go to, you know, I can go to system size 6, and then that won't be the smallest point anymore. So that's not really a systematic reason. But fine, you know, let's just say you extrapolate. I mean, it's still going to be fairly close in terms of the. I mean, I'll show you in the next slide what we get, but you know, just because it's the smallest isn't necessarily a reason to throw it out. You know, if you want to throw it out because it's alias, that's a perfectly justified reason. But just because it's small is not quite
You
as
can also say
justified.
it's justified because the others all line a single line, and this one doesn't.
Well, that's dangerous.
Yeah, I mean, if you applied that same reason to experimental data, you'd be in serious
It's
trouble.
very dangerous.
So,
That kind
I don't know.
of.
in any case, you know, this was all done for zero well widths, and you know, we're in the process of producing the same kind of analysis for finite well widths. But so here's some preliminary data that Gunnar has just recently produced, and here, you know, we actually don't have the n equals 8 point included yet. So that maybe makes you happy, but you know, what we see here is that actually, as you increase the well widths, you know, the shift equals 2 energy starts to come down closer to that of the shift equals minus 2 energy. But in any case, this is you know, very preliminary.
I think that's a very dangerous argument that you are just giving. I think they should all extrapolate exactly to the same. If you see, if one of them was a quantized state and the others were either quasi-Hall excitations or the one quasi-Hall excitation sitting on the quantized state, then the energy per electron would still extrapolate to the same thermodynamic limit. And it's a very dangerous,
For different well widths.
not for the same well width. You should still get a matching and then 1 over n equals 0, because they only
Of the
differ.
different shifts.
Yes, because a different
Well.
shift would. Maybe I'll talk about this at
Okay.
the end,
Sure.
because I think that is misleading. But
This is for the yeah, fine.
That's certainly true that you could really catch the infinite size behavior if you say those build the same thing.
I think I'll
That's right.
explain why I
Right, let's
why
discuss
I
it. Let's discuss that. So, okay, so of course, you know, numerics is actually, you know, a very nice, helpful tool to try and give us some perspective on what's going to happen. But ultimately, what we really want is experiments telling us what we have. So just to run through the list of experiments, which in my mind are we're thinking about for probing the nature of the topological order of states. You have experiments that can measure the quasi-particle electric charge, and these will tell you something about the states that you're observing, but probably not very much. Now, if you can actually measure the scaling relations from that you get in tunneling experiments, this will tell you a lot more, but these kinds of experiments also have a problem that universality seems to be not so present, because you're dealing with edge physics, which a lot of times can have some very non-universal effects in them. Another type of experiment that, well, I'll also say more about these in detail later, but another type of experiment is heat transport, and this will tell us something potentially important. And of course, my favorite is the experiments that probe grading statistics, in particular things like interferometry, because these tell us almost everything we want to know about the topological order. There's also Coulomb blockade type experiments, which actually they end up telling us practically nothing about the topological order, and I will say something about that first, because that's actually kind of a new result that I have. And there's also other kinds of experiments like lag scattering, which I actually have absolutely no understanding of what they tell us. So, but there's potentially other experiments not on this list which could tell us something important. So, first of all, let's look at the Coulomb blockade experiment. In particular, what you have in this situation is you basically have some Hall fluid, which is this hatched region, and you introduce two pinched off, two gates on top of it, which pinch off this this puddle in the middle from the rest of the Hall fluid. And if you have pinched this off sufficiently, you're basically going to stop the edge current that's running along here from going through to the other side of the Hall bar, except for the fact that you're going to have some tunneling between this edge on the left and the puddle, and also this edge here and the rest of the Hall bar on the right. And so by tunneling through this dot, you'll have some small amount of current getting through. And as it turns out, if you change the area of your puddle during the course of the experiment, you'll see a pattern arising in the tunneling current that you get, because you're gonna have a dependence on the current. The current will have a dependence on the area, which will find some points of resonance where it's easier for electrons to tunnel through than it normally would be. And in particular, the way to compute this, the points of resonance, is you look at the energy for the puddle in the middle for a different number of electrons. And here I've given the energy that you have for the edge excitations, and it's determined by the number of electrons you have, the B field, the area of the puddle, and the total topological charge that you have in the bulk, which I am denoting this way A and E, because this quantity depends on the total number. So each electron carries some topological charge A sub E, and if you have n of them, you're going to take a power. You're going to multiply that topological charge by itself n times, and then you're also going to multiply that by the topological charge, total topological charge of any quasi-particles that were sitting in this puddle region. And so this gives you the total topological charge of the puddle, and that will determine what the quantities on the right here are, which, so what you do is you're basically summing over all the edge modes, here designated by beta, and v is the velocity, L is the length, is the perimeter length of the puddle, and h is essentially sort of an effective conformal weight for the different modes, where I guess this A here should have been A sub NE, but in any case, you can you can think of these effective conformal weights as essentially the conformal weights of the CFT, unless there's any kind of symmetry breaking of the conformal mode. In particular, if you look at the charge mode, you can basically replace this effective conformal weight is equal to what you would have had from your original conformal weight modified by the sort of charging energy that you get by being at an area of the puddle which is not at the minimal energy that it should be in order to have that particular topological charge sitting on the edge. And in particular, you can rewrite this charge mode central charge in a more transparent form, which is just the you take the square of the number of quantized fluxes, which is given by the number of electrons divided by the filling fraction, plus the number of fluxes being carried by the quasi-particles in your puddle, and you subtract from that the number of fluxes given by your B field, and then S is just some sort of constant shift that would make it zero when you have a zero topological charge on the edge. And so you take that quantity square and multiply by filling fraction divided by 2, and that gives you your effective charge mode conformal weight. And then you'll find your tunneling resonances when you have the edge energy being equal for having two different values, n and n plus 1 of electrons in this puddle. So that makes it easy for electrons to tunnel in and tunnel out. That's the idea here. And then you can use the previous expression to write the spacing in as you vary the area of the puddle between resonance peaks, given by this expression, where if you just dropped off this part on the right, it would just be the naive area that you would expect each electron to occupy. So it's the electric charge divided by the charge density of the state in the puddle. And the part on the right here basically gives you the modification that gives you deviation from the naive spacing given by the neutral modes of your quantum Hall state. So here you have the neutral velocity divided by the charge velocity, and this delta square h is given by this expression, where it's basically the conformal weight for the charge you would have at one higher electron number plus one lower the conformal weight for one lower electron number, and minus twice the conformal weight for the electron number that you're at, and that'll give you the spacing. So all you really need to know in order to compute the spacing between resonance peaks that you would have as a signature for Coulomb blockade experiments is the conformal weights of the neutral sectors of your quantum Hall state and the fusion rules. And when you have those two, everything else is just easy to compute using this formula here. And based on the fact that you're basically describing the signature by this combination of conformal weights of neutral modes and not anything more inherent to braiding statistics, I argue that this is actually a very bad indicator of topological order. And in particular, you can have states at the same filling fractions with dramatically different braiding statistics producing exactly identical Coulomb blockade signatures. In particular, I call such states doppelgangers because that's the idea is they look alike. And for the the entire read-reside sequence has doppelgangers given by the k component m+1 m states, which occur at exactly the same filling fraction and produce exactly the same Coulomb blockade patterns. And more significantly to our discussion on the 12th state, we can look at the BS candidates and the anti-read reside candidate and see that they also produce exactly identical Coulomb blockade patterns. In particular, the spacing on the left here is when you have, for the BS states, an even number of sigma quasiparticles in the bulk, and the delta A1 here is for when you have an odd number. And for the anti-read reside states, the delta A naught is when you have a total topological charge that is not of the Fibonacci type in the bulk, and the pattern on the right is when you have a Fibonacci type total topological charge in the bulk of this puzzle. Okay, so moving on quickly, so there's the, of course, tunneling experiments at a single point contact, which, if you look at shock noise, will give you quasiparticle charge, but more significantly, if you look at the scaling relations, so you have current, which is going to have some non-trivial dependence on the temperature and the voltage that you apply at the gate, which is related, which the powers of that occur in these expressions are related to the conformal scaling weights of the various excitations in your quantum Hall state. In particular, so that G is this column here on the right, and you can see that for the hierarchy state you have the E/5 quasiparticles tunnel with a 3/5 conformal weight G, whereas the two E/5 quasiparticles tunnel with a 2/5. So based on that, you expect that as you go to lower temperatures, you're going to have the current being dominated by the 2/5 charge, but that's this is of course something that has to be done in the weak tunneling regime to see this. I think you expect. And similarly, you have these different values of G for the various candidates, and in principle, this might be a way to help you try to distinguish them. But actually, it turns out when you look at the experiments, it looks like there's a lot of non-universal physics going on. These are what you would expect based on universal physics of the technical. So, okay, so another form of experiment you could do is heat transport, where you basically use some method of introducing some kind of thermal, you put in some heat in some place and see if it propagates down to the left or right, and try to measure the thermal conductivity. In particular, doing this measures what's called the chiral central charge of the state, as given by the expression for the thermal conductivity, and comparing the 12/5 candidates. Well, you would add 2 to these to get to be in the 2 plus 2/5. But you can see these all have different values of chiral central charge, so this could, in principle, also be used to distinguish states.
I have a question about that, because I think you're referring to the devices.
Yeah, so
have you been able to extract for nu+1 the right central charge there?
yeah, I actually don't remember for sure. But yeah.
This might be
Yeah.
very hard as well.
This is probably
It's the only thing
this
I
is
wanna
probably is also as problematic as tunneling experiments. I absolutely agree. And so now finally we come to the interferometry type experiments done by, which has been done recently by Willett for the 5/2 state. And in particular here, so this problem has been analyzed over the years by many people, including myself, several times. As Curl says, it's not important who's said it first, but who said it last. And so far that's actually us. But anyway, the point here is that you basically form these two pinches in the edge, and instead of pinching it all the way off, you want to pinch it just enough to induce tunneling between one edge and the other at these two locations without killing entirely the Hall fluid between these two regions. And then you can measure the tunneling current and see what kind of signatures of the quantum Hall state you find in there. And in particular, you have the quasi-particles running along the edge, which they'll tunnel across the two ways in some hopefully coherent manner that does interference and then runs out. And so basically, you're going to have a very prototypical type of interference experiment around this middle region here, which in principle will depend on the area and the number of, the types of quasi-particles inside and so on. And the expression you get for the tunneling current is basically, it's what you'd expect. You have some probability of some amplitude of tunneling at the two different point contacts, and that gives you probabilities plus some interference term here, which the interference term has part of it which is essentially a phase that can be varied, which is this beta term, which you experimentally vary. It includes the Aharonov bone phase, and so you can experimentally vary it by adjusting the area of this by using some side gate to shove in the edge a little bit or pull it out as desired. And that's not something that's particularly surprising, but what's actually important here is this quantity m sitting out front, because this is actually something that has a very strong signature of the topological order of your state. So, in particular, this quantity m is related to something known as the topological S matrix of the theory, and essentially, if you want to interpret these diagrams physically, what you would say is that it's the component of the process wherein you braid two anyons around each other that leaves your state unchanged. So the important takeaway message from this, of course, is that this quantity m is just some abelian phase. It's just some phase when it's an abelian braiding of the quasi-particle types A and B, but it actually has magnitude less than 1 if and only if the braiding is non-abelian in nature. And so this is a smoking gun of non-abelian statistics.
How much smaller than 1?
This is exactly what we'll see right now. So now if we look at the Moore-Reed or the hierarchy states built on Moore-Reed, these will have Ising type or SU2 level 2 type anyons, which have these 3 particle types I mentioned before. And here's the matrix M for these particle types. You have I, sigma, and psi in these matrix, and so you can see that if you have a sigma going around a sigma, you have complete suppression of this interference term. You have a 0. And of course, if you have this -1, this isn't something that gives you any suppression, of course, but it could be something you would observe as a pi phase shift in your interference pattern. So you can, in principle, see in two ways a signature of non-abelian statistics in the state. One is a full suppression of the interference term, and the other is these pi phase shifts. For the reader Xi states, which have Fibonacci type anyons, you can boil it down to essentially two particle types, one which is trivial and one which is non-trivial. And here, this quantity m has, for one of these non-trivial quasiparticles going around another non-trivial quasiparticle, you have a suppression factor of phi to the -2, where phi is the golden ratio, and in particular, that gives you a suppression factor of 0.38, approximately. Now, I'm running out of time, but I'm pretty close to being done, so I'll just power through if it's okay with everyone. An important part of interference is, of course, that it needs to be coherent, and another important point here is you can have tunneling of quasiparticles which are not the fundamental quasiparticles, and these will, in general, occur with independent amplitude. And this kind of tunneling could potentially dominate the interference signal depending on what regime you're in. And the way that this basically boils down to is there's another piece of information which is important to consider, which is the coherence factor of the edge excitations around this interferometry region. And it's given by essentially an exponential dependent on temperature, and L here is actually half the length of the interferometry region. And then this quantity here on the right, which is the conformal weight of the charge component of the charge mode divided by the charge mode, edge mode velocity, and the conformal dimension of the neutral modes divided by the neutral mode velocities. And in particular, estimates for these velocities coming from numerics by Juan et al. Indicates that the neutral mode is about 1/10 as big as the charge mode velocities. So what that tells you is that, if you have too much weight, conformal weight of your excitations in the neutral mode as opposed to the charge mode, then they're going to have shorter coherence lengths or lower temperatures that you have to get down to in order to see the interference. Now,
Sorry, guys.
Yes.
This coherence factor will affect you, will prefactor in your interference formula, yes?
yes,
So
yeah, this will be a prefactor on the interference term.
Yeah, so how will you distinguish that this m factor is smaller than 1 because of non-abelian statistics or because of that?
By varying temperature.
Yeah, but maybe there are some other sources of decoherence, like scattering and impurities. And so
Yeah,
on.
there could be other. There can always be other factors that show up. But when you see something that, when you're working at a particular temperature or whatever, and you're seeing interference, and then you're seeing the interference disappear without changing the temperature, you're just changing the area. This is something that you can treat the Q as being some fixed constant. So it's not really going to be, you can have some decoherence, but you can still extract what the M quantity is.
So my question was precisely, can you measure it in the experiment rather than calculating it? I mean,
Measure what?
Decoherence term. Then you can.
Well, presumably it's something that you can observe by, changing temperature or whatever.
Then you can subtract it from.
Yeah, because you're going to have you can measure the total tunneling current, and then you can measure the amplitude of the interference current, and you can compare.
But so first you need to get rid of all quasi-particles inside for the. No, you don't.
No, that's not an issue at all. Okay, if you're dealing with something like the Ising case, and you have an odd number of quasiparticles inside, you won't have an interference term. So that won't actually tell you what the magnitude of your interference term, of course. But you can change the number of quasiparticles to an even number of the sigmas, and then you'll see a current in the
Yes.
extract.
So my question is, how do you find what is M there in the interference term? How do you subtract it from incoherence factor?
Well, by changing the number of quasi-particles.
It's
Maybe it's this is not an additive thing, so this is a factor in front of both behaviors. So if you just change the size of the interference region, then you'll see this on-off effect, right? The interference is on or the interference is off. That's how you extract that there's this zero in the M matrix, right? If it's off, if you see it just turn off, there must be a zero in the M matrix. This thing is a prefactor in front of both regimes. So if this thing is too small, you don't see any interference at all. But obviously, it's not something that is. If this thing is not too small, then you can just get the M out regardless. And this is the same factor in both regimes, even or odd number of the particles in the interval.
Yes, it's exactly my question.
As far as you're concerned, there is just a constant. I mean, it's not.
It's just going to be a multiplicative constant on
Yeah.
your interference.
Yeah, it's a constant, but you need to know it to find out what is M.
No,
You
you
don't
don't
know
know
to see the on-off effect. It will affect the visibility that the effect will still be there.
The matrix elements of M gives you the reduction. You go from one number of quasi-particles to another number of quasi-particles. There's a further reduction for any number of quasi-particles, which is this factor, but that doesn't matter because that's an overall constant.
We should discuss that.
Yeah, we should.
Okay, so then the point then is that you can look at this and see and try and make some prediction as to what quasi-particle types are going to show up in your tunneling current signal. And so here we have the two columns G charge and G neutral, and in particular what we can see is that we'll always expect the Laughlin type quasi-particles to be present, and so these are always here as the abelian type of 2e/5 quasi-particles, and this will form essentially a background that will always occur. It might be something very small based on what the tunneling amplitude for this quasi-particle type is, but it should essentially always be there. And then the question is there something that is there a quasi-particle type which is going to have stronger tunneling as you go to lower temperatures, meaning a lower total G, which might emerge in the interference term as a result of the coherence increasing. So here you see that you expect that you'll generally have more tunneling for the BS state of the non-abelian quasi-particle as you go to lower temperatures, but it'll also be something which picks up in coherence as you go to lower temperatures. And similarly, you expect this kind of behavior for the other type of BS state and also for the Reed-Rezai states. But then you can see that the way you'll distinguish things is based on whether or not you're seeing this behavior of non-abelian nature from this M quantity, where here, you'll just always have, if you're seeing E/5 oscillations in your pattern, they won't come and go because they're simply abelian, whereas here you'll have, you'll have some E/5 patterns that don't disappear, but you'll have some of it which will just come and go, whereas in the Reed-Rezai state you'll have E/5 oscillations which are always going to be suppressed by exactly this 0.38 amount that you have from the non-abelian nature. So that'll give you a way of distinguishing between these states. Okay, so basically to sum up, we've produced hierarchy states that, it takes the pairing nature of the 5-half state as its the fundamental physics, and produced states occurring at filling fractions of all the second Landau level states, in particular the 12/5 and 7/3 and 8/3 states, and occurring at the first level of hierarchy. So it's sort of the first things you get out of the hierarchy construction. And the point to emphasize here is that now HH and RR have competition from BS at 12/5, and it's actually a very interesting problem to figure out what is actually physically going to be observed there. And unfortunately, if read reside turns out not to be observed there, this will be sort of a challenge for topological quantum computation, because you won't have the nice Fibonacci type anyons. However, Ising anyons wouldn't be so bad, So if we have the more read state or the BS states, we could actually use them to some extent for topological quantum computation. And in particular, you should go to Kirill's talk tomorrow, because he'll tell you exactly how we would be able to use them to produce universal quantum computation. And of course, the first attempts to experimentally determine the nature of these states are underway, so we should hopefully know more soon. Thanks. So I should also say that Rudy actually has some slides that he would like to show on 12/5. So maybe we can show that now and then go to questions, or what would work best? So I'll let him take over.
So on the left, we look at the ground state energy versus system size. On the right, it's the energy of the largest exciton that we can form from a 1/5 quasi-hole and quasi-particle in the Reed-Rezai shift. When I say it's the Reed-Rezai, of course it's Coulomb ground state, but for the quantum numbers for which the Reed-Rezai state would be applicable. And one comment, typically what we see for quantum Hall states is that for all sizes where the state can occur, namely in this case for even sized systems, we observe L = 0 ground state, and the energy versus system size is fairly smooth typically. If we look at 1/3, if you look at 2/5, if we look at U = 1, is just a wonderful smooth curve as a function of 1/n with very, very small oscillations, extremely small oscillations, and a very small 1/n square contribution, which is basically the 1/n itself is basically a curvature effect of the sphere. And if we don't have at the same time varying density because we don't scale the sphere radius properly with system size, then the 1/n correction is a very small effect typically. Now, when we look at the excitation spectrum for the longest wavelength exciton, we usually see oscillations which come about from commensuration effects. I briefly commented on that 2 days ago. That is what we see on the right. It's not a particularly nice, but it's not a particularly bad example either. I would say looks plausible, but of course we have no idea if the gap in the thermodynamic limit is rather 0.02 or 0.04 E square over epsilon L. Now if we go to the second page, is the quantum numbers of the bonderson quantum numbers that we have now heard about. And Steve pointed out if we omit the lowest point, I use a little bit, my graph shows the deviations much more clearly, because I am using a scale where all these 1/n corrections show up very, very distinctly. And as you can see, the extrapolation that we perform is very different. It varies between 340 and 344, depending on whether we use the 8 electron result or not. But we should not forget that we have already an estimate for the thermodynamic limit from the previous slide. And in the previous slide I showed two extrapolations, one based on the lower, smaller 8 points, and the other one on the larger 8 points. It's a very, very small difference. So if we use that extrapolation, we can kind of decide that the bonderson extrapolation should be the one where we do include the 8 electron result. But this is just a remark. I would generally say that if I see a behavior like this for the ground state energy, I would be somewhat suspicious that there are defects present in this system. I'm just saying I would be slightly suspicious. Now I come to this point about the intercept, that the intercept should be the same for the two values of S. If there is only a constant number of quasi-holes difference between the two states, there is a finite order 1 energy difference, which after dividing out the 1/n will scale to 0 in the thermodynamic limit. So we always expect for states that differ by a constant shift, not the one that scales with n, but constant, we should see the same intercept. So typically what we would then say, this deviations from a smooth curve might reflect some interaction effects between quasi-particles or quasi-holes in this system that would be present. On the other hand, we see large gaps on the right, although they don't seem to have a nice behavior as we change system size. It's by no means clear what we should do with them. Should we extrapolate to 0? Should we extrapolate to 0.02? I have no further comment than it looks a bit odd.
Well, it looks odd, but no, on the Steve's side, if I look at that data, the 1/8 point is clearly an outlier. The gap is heavily underestimated for some reason, it looks, and that is of course because the ground is overestimated. That's why it's on the left.
Well,
so that's a good reason to skip that point.
What is the physical reason for this point?
Exactly that. It's not in the finite size scale.
But can you check it for bosons, for example? Do you have similar wave function for bosons? Then you can also see, do you have these points or not?
See, we know that finite size scaling is not present at all. System size is also.
Of course.
So there's a small system size of finite size scaling just apply to because we're not in the scaling regime. Now it's hard to argue that just a term or whatever. So the way we do that is we look at the data, see whether it looks reasonable or not. And so what makes us think that this last point is business? So
Which geometry is it? Is it torus?
No, it's a sphere.
You can't do it on a torus.
Of course we can do it on the torus.
But then you can compare.
Yes, of course we can compare, but I did that explicitly for this conference. I worked out the 16 electron result for the real quiz. The 16 electron result for the PS state I had already done in in spring of this year. And to me it is inconclusive, but I wouldn't bet on a state that has so much it's not understood finite size effects. I think if we understood these finite size effects, we could argue one or the other way. But without understanding the finite size effects, I personally think finite size effects are extremely interesting. One should explore them, one should understand them, one should have an idea what causes them, and then one gets an even stronger argument in favor of one or the other.
So if you work on the torus, you don't have a shift.
Right.
So you know, you expect both states will be there, and actually in the 13 Rezai and Reed's work at 13th, you see that the lowest states seem to be the degeneracy of the Rezai, but then if you look in the excitation spectrum, you find the states that and there hasn't been overlaps done or anything like that, but states that look like they have the right quantum numbers with the S states in the lowest excitations. But the problem is then doesn't seem like a very nice way to do a scaling to the thermodynamic limit. So you can't say necessarily that there's no crossover or anything.
This is all for Coulomb interaction. Yes, if you shift a little bit from Coulomb interaction, do you still have this point here?
Actually, I haven't done the whole analysis for finite width, but there is one very interesting observation. I can, of course, use the Coulomb ground state and exciton state to estimate the gap of a system with a finite width, where the interaction reflects the finite width of the wave function in the direction perpendicular to the plane. And the wave functions change quite dramatically. I would say in this, actually that was in the Reed-Rezai state that I did, but I have not looked at it for the BS state, that the wave functions change dramatically is perhaps an interesting signal that we might not always see the same state. We might in some cases see BS and in another case Reed-Rezai. And both would be interesting, of course. And the hierarchy state, that's again in the spirit of reasons to be hopeful. The hierarchy state is almost ruled out in the second Landau level. I think there is no, you can tweak the interaction how much you like. The hierarchy state is not going to be the ground state. And so that's a reason to be hopeful. 2/5 is seen in the second Landau level. Hierarchy doesn't work. The ones we have seen would be much more interesting.
Any questions for the speaker?
I actually have a question, if I may.
Sure.
You had this graph, this table of what you would see at low and high temperature, the G's that come in, and for the Reed-Rezai state, the particle Hall conjugate Reed-Rezai state, you have the same 2/5. So at low and high temperature, you would see the same G.
Yeah.
There's
So
no crossover.
so G is the same.
Right.
But the non-abelian
Of course.
quasi-particle has
Right.
the G is split up into charge and neutral parts, so it will have less coherence.
Right.
Yes.
So you would see, but how would that go as a function of temperature?
So it's the
Would we at very low temperature see the non-abelian signature?
yes, that's what you'd expect.
Because it's this coherence factor that
Yeah. So
becomes big if temperature is very, very small.
right. So this is the relation at a single point contact. So this tells you the total amount of tunneling of that charge type at both when you have two, and then you know, this is the coherence factor here,
Yes,
right?
which goes to 1,
And
and
then-
the temperature is very, very small.
And then when temperature gets low enough, then coherence gets better, and it gets you know, in particular, the coherence gets better at a higher temperature for the abelian particle than it does for the non-abelian.
Right. Because the slow velocity
Because of
is
slow neutral velocity.
right.
But of course, you have to be careful to do with high temperatures, right? Because the whole analysis is based on.
Yeah, if you're at too high temperatures, it's not so meaningful. But
I have two questions. Short. What is the largest size where you've got the spectral decomposition of the state? I suppose most of the results are Monte Carlo. For the actual state, not the Coulomb state. For the BS.
the trial state.
Yeah. What is the largest size which you've got the spectral decomposition of the state? Well, I mean, the expansion in Slaters, rather than the first one.
I don't ever calculate expansion coefficients of the Slaters.
No, but how do you do these overlaps by Monte Carlo?
Yeah,
Okay.
real space.
Okay, so you don't have.
Position space. I don't get all the, I mean, it'd be very difficult to get the overlaps right by calculating 1 million coefficients, right? If you have some small error, I mean, you have to have an error much smaller than 10 to minus 6.
No, yeah,
For that
there's
to be-
there's not millions, right? There's only
Well, of course there's a million.
L equals to 0 state. There's not.
But, well, I
So
mean,
you can explain it.
those are not
But
Slaters.
yeah, I agree. You answered my question. So, but the second question is regarding like this, what we were talking about, the quasi-particles. Which ones would you condense? Right. I mean, it seems to me that you can kind of take a finite size system with more read, put some impurities in it, like some one-body potentials, and then kind of crank out the density to go to your shift. Right, and you should see which quasi-particles. I mean, your talk seemed to say that it's very hard to break them apart. So in that sense, you can
No,
be
no.
condensing.
It's not very hard, but you have to do it right. Actually, you know, what I said was, if you couple to density, just to density, it's a problem because the density vanishes for the doubly charged one, whereas it has only a minimum for the at the position of the quasi-hole for the 1/4 charged one. Doubly charged would be a half charge, and the other 1/4 charged. Now, when you do it right, you may remember that I showed. Well, I really don't expect anyone to remember this, but you can localize them more strongly or less strongly in a wide range. In other words, the potential that you're allowed to apply to your gate can vary quite a lot. You don't have to be extremely careful. What you have to be careful about is how large the electrode is that you use to localize this quasi-hole. But the strength by which you localize it is very, very a perturbation that is very gentle, even if you localize strongly. What you might remember is that if one wants to localize it more strongly, then one gets more long wavelength oscillations. In other words, if it was Friedel oscillations, those would be more pronounced if I want to localize more strongly. So the actual size of the disturbance grows if I localize strongly. That is something that, but but it's not. It's easy to localize if you do it right. And so now comes the question: is there a density above which you'd only see the half-charged ones? That is an interesting question, and I cannot answer this question because I have been able. The braiding that I carried out, I've done for very different geometries, and it has been possible to collide them very, very close way, and you separate them very easily. You can control them very easily as individual ones without having this situation that like in soap bubbles, that when they come too close, that all of a sudden you'll get a big one. So it doesn't seem to be hard to keep them in two separate, although overlapping units. That is answering probably your question,
Yes.
more or less.
Any more questions? If not, I thank this